All right, super giant fun example. I am going to ask you two questions that aren't even on this first. So question number one. Question number -1. Here's a graph of a function f prime. So this is a graph of the derivative of f. And I will ask you this question. Where is the function f, which you can't see? It's the original function, but I'm not showing it to you, right? Where is the original function f increasing? See if you can answer this question before I move on. Here's my answer. Remember that a function f is increasing anywhere f prime is positive. So look at this graph, which is the graph of f prime. Notice any place where the graph is above the x-axis, and there's places where f prime is positive. So I said f is increasing when -3 is less than x, which is less than -2, and 4 is less than x, which is less than 5, because f prime of x is positive on those intervals. Notice you could have chosen to use interval notation, like parenthesis bracket notation, -3 to -2, 4 to 5. Those mean exactly the same thing. They get full credit. I'm making a point this year of using the inequality notation because I have some students who sometimes get confused and think that those are ordered pairs. So, but feel free, if you know that they're not ordered pairs, they stand for intervals, feel free to use that notation. And I will make a point here. Functions don't increase at one point and then decrease at the next and then increase at the next point. They increase over whole sections of the graph. So those are called intervals. And just to make sure, the preposition we use is on an interval. Something could happen at a point, but if something happens over a whole interval, we say on that interval. Have you guessed what question I'm going to ask you next? Question 0, where is the original function f, which you can't see, where's the original function f decreasing? See if you can answer before I move on. So my answer to question 0 is not actually printed on your page. Where would f prime be decreasing? F is, I'm so sorry. I think I really asked you what I meant to ask you just now. Where is f prime? No. Where is f decreasing? F is decreasing anywhere f prime was negative. So f prime is negative between -2 and 1, and then again from 1 to 4. So that's why I have these answers here. From -2 to 1 and 1 to 4. Notice instead of the word and, you could have made a union symbol here. That's just as good. Feel free to have used interval notation, but only if you promise that you know that it's an interval and don't get confused and think it's an ordered pair. And again, notice, whoops, not sure what that extra quote is for. On those intervals. I could have also used the word on here, where I use the word when. They would both be appropriate. Okay, so now onto the questions that are printed on your page. I'm going to erase these so I have lots of room. I'm hoping you're writing smaller on your paper than I'm writing here. All right, so here's the new stuff. Question 1, for what value of x does f have a relative maximum and why? So you could, if I hadn't asked you why, you could just give me a one-number answer or however many answers you think there are. But this why, that's where I want to know the calculus, is what I want to hear your reasoning. So what did we just learn? We learned the first derivative test for extreme relative extrema. So see if you can write up your answer to number 1. All right, so here's my answer. F has a relative maximum any place f prime changes from positive to negative. So here's f prime. It's only positive in a couple of tiny places, right? So f prime here was here was positive, and right here at x equals -2, it changes from being above y equals 0 to below. So f prime is changes at that exact point from positive to negative. So that's why I've chosen x equals -2. Is there any other time where the derivative, this graph, is positive and then changes to negative? No, because the next time it's positive, it continues on till the end of its domain. So f has a relative maximum at x equals -2 because f prime of x changes from positive, thank you for correcting my spelling, to negative there. Notice this word, at. Extreme values happen at single locations. Top of a hill is 1 point. The bottom of the valley is 1 point. So we use the word x and we list we use the word at and we list individual x values. So try number 2. For what value or values of x does f have a relative minimum? Well, that's sort of like that converse, right? F is going to have a relative minimum any place f prime changes from negative to positive. Where are those? Here, f prime is negative, 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 negative. Here it's 0, but it doesn't actually change sign, so that doesn't help us. We need to actually change from negative to positive. That only happens here at x equals 4. There's my write-up. F has a relative minimum at x equals 4 because f prime of x changes from negative to positive. Now notice that f prime of x equals 0 at x equals 1, but do we have a relative minimum or a relative maximum? We have neither one because f prime was negative. Where's the marker? Was negative here, negative, negative, negative. It touches 0, but then it goes back to being negative again. It doesn't actually change from negative to positive. There's no sign change. There's no extreme value there. Haha, I just noticed that question 4 was my question -1. But that's okay. You already know the answer now. Question 3, on what interval or intervals of the graph is the graph of f concave up? Don't go to this graph and try to do like umbrella up and, umbrella down and bowl up. This is not the graph of f. And if all you did was look at this graph and try to figure out where it was a bowl and where it was an umbrella, you're not doing calculus. Concavity is not a calculus topic. But using the second derivative to figure out where a function is concave up or concave down, that is calculus. So notice here we've been given a graph of f prime and I'm asking you a question about f. That's a little bit like having to underderivative something. So question 3, on what interval or intervals is the graph of f concave up? Well, before we try to answer that, what do we know about concavity? You wrote it on your paper. There's a place for you to write it in your 19 facts paper. The one thing you know is that f is, I'm going to write this out, concave up. You probably don't have to write this out. You're going to wait until we do a write-up. But I'm just like notes here. F is concave up where f double prime is positive. That's what you memorize. That's what you know. That's what you put on your 19 facts paper. That's awesome. It's not helpful here yet because I didn't give you a graph of f double prime. If I showed you f double prime, you just look for where it's positive, and that's where f is concave up. But that's a problem. We don't have a graph of f double prime. All you have is a graph of f prime, and we're going to have to be able to use that to figure out where f double prime is positive, which will tell us where f, the original function, is concave up. So just notice that we can sort of stack these derivatives, right? What do we know about f double prime? It's the derivative of f. So f is concave up where f double prime is positive. Well, where is f double prime positive? That's the same as saying where f prime is increasing, right? Because where is f prime increasing? F prime is increasing where its derivative, f double prime, is positive. So that one works both ways. That's a converse, that's a biconditional, I guess is a fancy word for it. A function f is function f is increasing where f prime is positive. And wherever f prime is positive, f is increasing. Works both ways. So that's what I'm going to have to figure out. And the good news is I actually have a picture of f prime here. If I can just figure out where f prime is increasing, I'm going to have the same answer as where f double prime is positive, which is what I need in order to conclude that f is concave up. So I'm going to circle the places where I think f prime goes uphill. All right, that's from -1 to 1 and 3 to 5. Now I'm going to give my write-up. Notice I'm going to base my write-up on the behavior of f prime because that is what I have a graph of. That's the only evidence I have. But I still have to know that the whole reason this works is because of what I wrote down about concavity earlier in my notes, which is that f is going to be concave up, where f double prime is positive. So I write that f is concave up on -2 is less than x, which is less than 1, and 3 is less than x, which is less than 5, because f prime is increasing on those intervals. Okay, here we go. Now one more. Got number 5. At what value, because we said number 4 I accidentally already gave you the answer to, right? So number 5, at what value or values of x does f have a point of inflection, and why? So you wrote down some stuff about a point of inflection. Where does a point of inflection occur? Any place where f double prime changes sign. I'm going to write that down before I forget it. F double prime changes sign. Okay, that's great, but again, I have a similar problem, which is nobody gave me a picture of f double prime. So you could try to sketch one to get an idea, but we want to connect this idea, we want to use this idea of f double prime is the derivative of f prime to sort of string these properties together and see if we can get an answer. Well, where is f double prime going to change sign? Well, f double prime is positive where f prime was increasing. That's what we just said on the last for number 3, right? And f double prime is negative where f prime is decreasing. So for something to change from positive to negative, that could happen where f prime changes from increasing to decreasing. Similarly, it can also happen where f prime changes from, whichever the one is the other one. So f prime, anywhere f prime changes from increasing to decreasing or decreasing to increasing. So I had earlier circled places where f prime increased, was there, increasing and increasing. So at this place, f prime changes from increasing to decreasing. And does this function ever change from decreasing to increasing? Here's where it's decreasing. Okay, so right there, from decreasing to increasing, from right here, from decreasing to increasing. Those are going to be the 2 locations of my point of inflection. Why did I make you write about f double prime on your 19 facts paper if we're going to use f prime? So we're using what you know about f double prime. A function f has a point of inflection where f double prime changes sign. We just don't happen to have access to f double prime in this particular case. Sometimes they would do that on the AP test, but they usually have to make you have to work a little harder. So we sort of stacked our derivatives together to think about what would have to be true about f prime in order for f double prime to change sign. Well, let's bring back in what we learned from 4.2, which is a function is increasing anywhere its derivative is positive. So f prime is function is increasing anywhere its derivative is positive. So f prime is increasing implies that f double prime is positive. And then to change from positive to negative or negative to positive, we conclude that happens. You could think about it as where the direction changes, but it's really more, if you would just write that, that's not correct. This is specifically changing from increasing to decreasing or decreasing to increasing. I'll show you the write-up. So there's my write-up. F has a point of inflection at x equals 1 because f prime changes from increasing to decreasing there. Again, thank you for excusing my spelling. F also has points of inflection at x equals -1 and 3 because f prime changes from decreasing to increasing, thank you, at those points. Again, thank you for excusing my spelling. This is not uncommon. I don't know that they would ask you all 5 of these things, but it's pretty common to see a free response question that includes 2 or 3 or 4 of these kinds of questions. So you've been given the graph of a derivative and you get grilled about what the original function looks like. They could ask you about points of inflection, could ask you about concavity, they could ask you about increasingness or decreasingness, and absolutely relative extrema.